Challenger did not fail 73 seconds after launch. Its final chance of survival disappeared the night before. Engineers warned that the shuttle's rocket seals had never faced the cold waiting at Cape Canaveral. The recommendation was simple: do not launch. Hours later, the recommendation had been reversed. The weather had not improved. The design had not changed. Only the decision had. On 28th of January 1986, ice covered parts of Launchpad 39B. At 11:38 that morning, Space Shuttle Challenger lifted away from Florida. 7 people were aboard. Among them was Krista McAuliffe, the teacher selected to give lessons from space. Schools across America were watching. For the first minute, the launch appeared normal. But the failure had already begun. Just 0.678 seconds after ignition, cameras recorded black smoke escaping from the right solid rocket booster. NASA had seen damage in this joint before, more than once. The smoke stopped. For almost another minute, Challenger continued climbing. Then, at around 58 seconds, a flame appeared from the same booster joint. It struck the external fuel tank. At 73 seconds, the tank failed. Challenger broke apart. The image became one of the defining disasters of the 20th century. The accepted explanation is that cold weather caused an O-ring to fail. That is true. But it is only the final link. An O-ring is a flexible rubber seal. Challenger had 2 solid rocket boosters attached beside its external fuel tank. Each booster was built from large steel sections. Rubber O-rings sealed the joints between them. When the booster ignited, internal pressure caused the steel casing to flex. The joint opened slightly. The O-ring had to expand quickly enough to keep the opening sealed. A warm O-ring could respond. A cold one moved more slowly. On the morning of the launch, parts of the failed joint may have been below freezing. The rubber was stiff. It did not seal quickly enough. Hot gas escaped. That was the physical failure. But that was not where the disaster began. The booster joint had a design weakness. As pressure increased, the metal joint rotated. That movement could pull the sealing surfaces away from the O-rings. There were 2 rings, a primary seal and a secondary seal. That sounded like redundancy. It was not. If the primary ring failed to seal quickly enough, movement in the joint could also prevent the secondary ring from working. NASA classified the joint as a criticality 1 component. A single failure could destroy the vehicle and kill the crew. There was no reliable backup. Then came the evidence. O-rings showed heat damage on previous missions. Some were eroded. Some allowed soot and hot gas beyond the primary seal. In January 1985, another shuttle launched in unusually cold conditions. Its booster seals suffered the worst damage yet recorded. That launch took place at around 12 degrees Celsius. Challenger would launch in conditions far colder than that. Tests had also shown that cold rubber recovered slowly after being compressed. The warning was no longer theoretical. The seals were sensitive to temperature. The joint could open before the rubber moved into place. Hot gas only needed one path out. The problem was visible, but each successful launch made it appear less dangerous. Damage was found. The shuttle survived. So the damage was labelled acceptable. Soon, a warning that should have stopped the program became part of normal operations. Repeated survival was mistaken for proof of safety. But surviving a risk does not make the risk smaller. It only means the worst outcome has not happened yet. By July 1985, Morton Thiokol engineer Robert Boyce-Jolly was warned that failure of the booster joint could cause catastrophe and loss of life. A task force was created. The joint was discussed. Changes were proposed, but the shuttle program continued launching. The flaw had become familiar, and familiar danger rarely feels urgent. Then came the evening of 27th of January 1986. The forecast predicted exceptionally low temperatures. Engineers from Morton Thiokol, the company that built the boosters, joined NASA managers in a telephone conference. The engineers presented the previous O-ring damage. They explained that cold rubber would seal more slowly. They recommended the Challenger should not launch below 12 degrees Celsius. That was the coldest condition supported by previous flight experience. The forecast was far below it. The initial recommendation was clear: do not launch. NASA managers challenged the evidence. They questioned whether temperature alone proved the shuttle was unsafe. Thiokol's managers paused the conference for a private discussion. During that meeting, engineering judgment gave way to management judgment. The company returned with a new recommendation: launch. No new test had been performed. No new evidence had appeared. The temperature had not changed. The burden of proof had been reversed. NASA no longer had to prove Challenger was safe. The engineers had to prove it would fail. They could not prove that. No one could know exactly what would happen inside the booster after ignition. So uncertainty became permission. That was the central failure. A lack of proof that Challenger would fail was treated as proof that it was safe. Senior launch officials did not receive the full picture. They were not told that Thiokol had first recommended against launch. They were not told that engineers still opposed the reversal. The warning reached management. The opposition behind it did not. This was the last preventable point. The launch could still have been delayed. Nothing required Challenger to leave Earth that morning. The crew was ready. The payload was ready. The schedule was waiting. The seals were not. At ignition, pressure built inside the right booster. The joint opened. The cold O-rings failed to follow it quickly enough. Hot gas passed the primary seal. Black smoke escaped almost immediately. Debris may then have temporarily blocked the opening. For almost a minute, that fragile seal held. Then, the shuttle passed through stronger aerodynamic forces. The blockage was disturbed. A flame cut into the external tank and weakened the booster attachment. The fuel tank began to fail. Challenger was torn apart by forces it was never designed to survive. The final event lasted seconds. The chain behind it took years to build. A flawed joint was accepted. Seal damage became routine. Repeated survival became reassurance. A warning was challenged. An engineering recommendation was reversed. Critical information failed to reach senior decision makers, and uncertainty was used to justify action. The O-ring caused the physical failure. The cold exposed the weakness. But the catastrophe required an entire decision system to ignore what the hardware had already been saying. Challenger did not fail because nobody saw the danger. It failed because the danger was seen, discussed, and gradually made acceptable. Francis Scobie, Michael Smith, Judith Resnick, Ellison Onizuka, Ronald McNair, Krista McAuliffe, Gregory Jarvis. They were not lost to one defective seal. They were lost to a chain of decisions that allowed that seal to become the final point of failure. The same pattern would appear again. In aircraft, in bridges, in machines whose warnings arrived before their collapse. The collapse came later. The failure began earlier. That is the failure chain.